All right, here we are with complex numbers, day 2. Notice the slightly modified objective. We were really just going over the basics of complex numbers in day 1. We did a little bit of addition and subtraction, and today we want to multiply and divide. Okay, this is for some reason in the format I have this in. This piece right here is just not coming out correct. So disregard that and rewrite that I squared equals -1. We went over those fab 4 powers, those 4 powers of imaginary numbers, which I suppose in the margins I could put in here. You know, the square root of -1, that's I. I squared is -1. I to the third is -I, and I to the fourth is 1. And then when we get to the 5th power, that is the same as I to the first, and it repeats. Okay, I squared equaling -1 is kind of a special one because it comes up a lot. Okay, it comes up an awful lot. If I had 4i times 5i, so I have two numbers that are just strictly imaginary. All right, those don't have a real component. That would equal 20 times I squared. Okay, again, I is not a variable, but as far as properties of exponents go, you can kind of treat it like it is. Okay, I times I is I squared. But I'm not going to leave my answer like that because I could rewrite that as 20 times -1. Which is actually -20. So that's an interesting little example where we see that the product of two imaginary numbers, in that case, ends up being a real number. Another example that goes to show that do not think of imaginary numbers as this completely contrived, system of numbers that's just way off and out there and has nothing to do with real numbers. They are very much related to real numbers because their existence comes from asking a fundamental question about a real number. What's the square root of -1? Okay. Here we have a real number 5 times a complex number 6 plus 7i, and we need to distribute. And when we do that, we get 30 plus 35i. And that is a completely acceptable form to leave our answer. Okay, because you remember in our hopefully if you saw it, either on the video or in class, that we're totally okay with complex numbers being in the form a plus bi. That as far as a final answer, that form is typically acceptable to use. Okay. Here we have the product of two complex numbers. Okay, and it comes out kind of like a FOIL problem. 4 times 3 is 12. 3 times 8i would be plus 24i. This is another kind of problem on these videos that it's not a bad idea. If you feel pretty confident in what you're doing, feel free to pause, work it out yourself, and see if our solutions match. -9i times 4 would be minus 36i. And then the last two terms would be -9i times 8i, which would be minus 72i squared. Make note of that I squared. That is eventually going to get replaced with -1. Now, as far as simplifying goes, I've got my 12. I'm going to leave that for the moment. 24i minus 36i, those are like terms. Okay. And over here, I will have minus 72, and I am going to substitute -1 in at this point. All right. 12 minus 12i plus 72. When I take -72 minus -1, I can add those real components of 12 and 72. I get 84 minus 12i. That's what I'm looking for with the real component and the imaginary. And I'm good. I'm good to go on that one. I am not going to take the time to work through this last one, but I do want to say that it's important to get started on that one. We have negative I minus I squared. It is very helpful to write that out like this. Remember, a squared term means whatever it applies to, we're multiplying that by itself. And the squared term applies to the quantity negative 1 minus I. So we have to take what's in the parentheses, multiply it by itself, turns into a foiling problem just like the one we did. So now I want to save a little time by skipping that one and going down to dividing. All right? We're going to divide numbers that have an imaginary component, and we need to rationalize our denominators. No i's allowed in the denominator. Not that much different when we rationalize with a square root, where there's no square root signs allowed in the denominator of the fraction. Here, there's no i's allowed. All right. So if I had something like 5i, I could multiply that by I over I, and I would get 5i over I squared. I should put a reminder on here, just like I did on the first slide. Don't forget that I squared is negative 1, because at the moment it looks like my denominator got worse. It did not, because at this point I can take that I squared out. All of a sudden my denominator is negative 1. That looks so much better. And in fact, I don't even need a denominator, because 5i divided by negative 1 is just negative 5i. Okay? That's one way to rationalize a denominator, to get rid of it altogether. Okay? Just exactly what I did there. Okay, next up, this next example looks a little bit different, okay, because there's not just an I on the bottom of the fraction. There's a real number, 3, plus I. We have a complex denominator because it's got the real component and the imaginary component. Okay? I'm going to head up top here for a minute and go back to these fill in the blanks to answer our question. Do we have a secret weapon? Yeah, we do. We have a great secret weapon. It's called a conjugate, and they're super sweet. If we have a denominator of a plus bi, we are then going to go ahead and multiply, getting carried away with my variables, not a plus bi, I can multiply by 3 minus I over 3 minus I. Notice how I took the expression, the number, the complex number, on the bottom of the fraction, and I took its conjugate. Okay? Same complex number, except I reversed the sign that's in the middle. Okay? Good things happen. I'm gonna jump down here a line. I'm kind of working vertically here, but as far as the numerator goes, I would simply distribute 6 over 3 minus I. I'm going to take care of that first just to get it out of the way. And I get 18 minus 6i. Okay? Now, the denominator. I have a complex number here and a complex number there, so it's really a foiling issue. Now watch what happens here. All right? 3 times 3 is 9. All right? That's a real number. That's good. Okay? I want real numbers only in my denominator. The outer terms is 3 times negative I, which will be minus 3i. Okay, I'm seeing I is down in the denominator. That's a little nerve-wracking, but As we move to the inner two terms, it's positive I times positive 3, which is positive 3I. That looks good because now I've got two i's of the same quantity but opposite signs. So it looks like those two middle terms are going to cancel. And then the last terms would be minus I squared. That's going to allow me to get rid of that imaginary component. Okay, jumping down one more line here, I've got 18 minus 6I over, again, those cancel, and the reason those middle two terms cancel is because I chose to use the conjugate. Okay, every time I do that, if I jumped ahead to this next one, just to illustrate the conjugate concept, I'd use 5 minus 2I over 5 minus 2I. Every time I use the conjugate, that component of those middle two terms with i's canceling always happens. Okay? And then what I end up getting here is 9 minus negative 1, because I squared is negative 1. And notice that the i's are gone. Completely and totally gone. Okay? Which is wonderful. I'm going to have to steal some space here from this last problem, which I'm not going to work through. You can try that one on your own. The only thing I'll add to this last problem, again, same kind of thing going on here. The only extra work is on top. It's also a foiling problem. The canceling action isn't going to happen on the top, but that's okay. All right. In fact, if you're feeling fairly confident with this dividing stuff, I'd recommend on your own. Give that one a shot. Okay, and then as always, you can bring back what you have to me in class, and we can look it over. Or if you don't want to wait that long, you could work that one through. Email me your answer, and I can take a look at it, maybe even tonight, within a few hours. All right? Not tonight, or whenever you're watching this. Okay? All right. Back here. 18 minus 6I over 10. Okay, not quite done because all of those components are divisible by 2. So 18 divided by 2 is 9. Just barely squeezing this in, minus 3I over 5. Okay, and that is sufficient to be done. Okay, I've got my rationalized denominator. I've got 9 minus 3I. That's perfectly fine. I can have the a plus bi form in the top. It's just the bottom that has to be rationalized. Okay? That is, I should say those. Those are the basics of dividing with complex numbers. Again, this piece comes up all the time. That we kind of set it up so that I squared show up, because then we get back to -1, we get back to real numbers, and good things happen. All right? That is all for day 2 of complex numbers, and that actually wraps up, our second and final lesson in this unit on complex numbers. As always, if you have questions, be clear on what they are. Write them down if you need to, and when we see each other in class, let's talk about what was not clear from this lesson. All right, we'll see you in class.